These are the two newest members of our class, and they will be helping us learn probability and probability distributions today. So let's get started. So in order to talk about probability distributions, we need to start by looking just at what probability is. So we've talked so much about statistics at this point, and the difference is that statistics looks at the past, whereas probability looks at the future. And there are two types of probability. And when I say it looks at the future, I'm going to use the word predicts. Okay. So when we look at probability, there are two types. There's classical probability and there's empirical probability. I don't think probability would be correct. Probability. Okay. And the difference is that classical probability is the possible outcomes for different events. Okay. So you're tossing a coin, you can either get a heads or tails. You're rolling a die, you could either get 1, 2, 3, 4, 5, or 6. Okay, so these are the possible outcomes for different events. The one that we're going to focus on, though, and we'll talk about classical probability a little bit more in a second, but we will be focusing on empirical probability. And these are observations in an experiment. To make this clear, let's think about tossing a coin. Now, most of you are probably familiar with the fact that a coin, we say, at least a US coin, has a heads and a tails on it. If we were to toss a coin 100 times, classical probability would tell us half of those times you would get a head and half of those times you would get a tail, because each individual time you're either getting a heads or tail. So classical probability would say, well, half of those times you should get a head. Empirical probability says, no, what we're going to do is we're going to toss a coin 100 times and see how many times we get a head. And it's not always going to be true that 50 times we're going to get a head. Sometimes it might happen that only once out of those 100 tosses do we get ahead. So empirical probability is really just trying it and seeing what happens. Okay, so let's take a second though and go back to classical probability. Okay, and this is really true for empirical as well. So I don't want to be too specific here, okay, because it actually would be true for both. So in probability, we have an event, okay? The event is the action. That's the easiest way to think about it, because some people have a really hard time identifying what is an actual event. and the event is always some sort of action. So that action could be, sorry, I didn't mean to do that. An action could be rolling a die. It could be tossing a coin. These would all be events. Sorry about that. I want to put it in black so that you know that here we're talking about an event. Okay, an outcome is a possible result of an event. So if the event is tossing a coin, then the outcome would be heads, or an outcome would be tails. Okay, and a sample space is all the possible outcomes. Okay, so let's just take the examples I mentioned. So let's suppose that the event is tossing a coin. This means that the outcome, one possible outcome, is getting ahead. That's one possible outcome. If we want all of the possible outcomes, we would call that a sample space. And the sample space is either a head or a tail. Okay, let's take another example. So the event would be rolling a die. The outcome would be one possible result. So let's say that the outcome is 2. Okay, we could get a 2 if we roll the die. And then the sample space well, we could get a 1, 2, 3, 4, 5, or 6. And this would be on a 6-sided die, obviously. Okay. And this might be something that all of you are already familiar with, but I don't think that you're familiar with the notation. So the probability of an event we would say is P of E. So the P represents probability, and the E represents the event. Okay, so for example, we might be more specific about tossing a coin. We might say, what's the probability of getting a head? Okay, what's the probability of rolling an even number? Okay, this would be the number of desired outcomes over the total number of outcomes. And when we say total number of outcomes, what that means is the number of outcomes in the sample space. So if we say the probability of getting a 2, well, the number of desired outcomes is just 1, and the total number of outcomes is 6. If we wanted the probability of rolling an even number, then the number of possible outcomes would be 3, because 2, 4, or 6 are even, and the total number of outcomes would be 6. So the total number of outcomes in the sample space is not going to change, even if the event changes. Okay. A couple of other things to mention. The probability of an event is always between 0 and 1, okay? And what that means is if it's 0, then the outcome is not possible. And if it's 1, then the outcome will definitely happen. So if the event is tossing a coin and getting a heads or tails, that's definitely going to happen. If the event is rolling a die and getting a number 1 through 6, the event is definitely going to happen. But if we say rolling a die and getting an 8, well, there's no way that that could happen because 8 is not on the die. So that would be something that's impossible, and the probability would be 0. Okay, so let's just write those few things down just so that you have it. So the probability of an event is between 0 and 1. If we were to use notation to write that, we would be saying 0 is less than or equal to P of E, which is less than or equal to 1, where 0 says the event is impossible, or the outcome is impossible, really. So rolling an 8 on a 6-sided die. That's impossible. Okay, and a 1 would be, it will definitely happen. Whoops, sorry about that. So meaning you would roll a 1, 2, 3, 4, 5, or 6 on a 6-sided die. One of those will definitely happen. Okay. And one last note, and I'm going to put this in red. You can have events that have a probability of 0, meaning they are impossible. You could have events with a probability of 1, meaning they are definite. Okay. Both of these extremes are rare when you're talking about things happening in the world around us and not something like this. But there are events that have no probability, and those are ones that happen in the past, because probability predicts the future. If it already happened, there's nothing to predict, okay? If you're watching a game that happened yesterday, there's no probability as to whether the team won or lost. It happened, okay? You may not know the outcome, but the event already happened, so there is no probability. We can't talk about it in terms of probability. Okay, the event that you're watching this video, there's no probability that you're watching this video. We already know you're watching it. Okay, it happened. So events that already happened have no probability. Not a probability of 0, because that's common confusion. Okay, so let's get into probability distributions. Okay, and we're going to look at discrete. We're going to talk about discrete random variable probability distributions. So just as a reminder, a random variable. So we're going to start talking about probability distributions. And before we do that, just a couple of quick reminders. Okay, so a random variable okay, sorry, this is kind of slow today. So a random variable is a process or variable with a numerical value. Meaning the outcome of an event, or sometimes you'll hear it referred to as an experiment, is numerical. Okay, so it wouldn't be like figuring out what type of pet somebody has, and it's cat, dog, snake, whatever it might be. It would be number of hours that somebody spends on the phone. This would be numerical. Okay, so your answer to the event, the outcome of the event, is numerical. Tossing a coin, it would be heads or tails. That's not numerical. But rolling a die, it is. It's 1, 2, 3, 4, 5, 6. Okay. Then we have two different types of random variables. We have a discrete random variable. So a discrete random variable says that the outcomes can be counted. In other words, you can make some sort of list. And we'll talk about that in a second. We'll talk about a couple of examples. And then you can also have a continuous random variable. And I'll get that out of your way in a second. So in a continuous random variable, the outcomes can't be counted. So you can't make a list. So just quickly, examples of discrete. The number of phone calls made in a day, we could count that. The number of people who can fit on a bus or on a bus. Or the number rolled on a die. These would all be examples of discrete random variables. For continuous, it might be the speed of a car on a highway. The amount of time spent in a hospital. These would be examples. The reason why we would say that these are examples is that one person may spend 3.87 days another could spend 11.23 days. It's not really countable because there are such decimals that sometimes you can't even round off. Okay, so speed of a car on a highway, it's not as simple as 65 miles per hour. You could be going a little bit more than 65 miles per hour. So we would call those continuous random variables. Okay, so because of this, we only look at discrete probability distributions. Okay. Okay, so let's actually get into the probability distribution right now. So discrete probability distributions have two requirements. The first one is that the probability of each variable or outcome and if you remember, we call those x. Okay, and I'll put that up here too, a random variable x. Okay. It has to be between 0 and 1. Okay, in other words, it either doesn't happen at all, or it definitely happens, or sometimes it happens and sometimes it doesn't. That's what between 0 and 1 is. And then the second thing is that the sum of the probabilities is 1, meaning at least one of the outcomes has to occur. Okay, and the way that we write that is, some of you may know this, some of you may not, but the sign for sigma is this, the sign for sum is this uppercase sigma. So we're saying the sum of the probabilities is 1. Okay, so if we roll a die, we must get a 1, a 2, a 3, a 4, a 5, or a 6. We have to get one of those 6 numbers. That's what this is saying. And that's how we verify that we have a probability distribution. So let's take some examples of probability distributions, and we're going to use this to help us to answer a variety of questions. Okay, so let's start with verifying that we have a probability distribution. So here's our random variable x, and here's the probability of x occurring. So let's say that the different outcomes are 1, 2, 3, 4. We don't even care what the event is right now. We just care about whether or not we have a probability distribution. And the probability of getting a 1 is 0.09. Probability of getting a 2 is 0.36, a 0.49, and a 4 is 0.10. And I just made these up, okay? I just made them up. So you don't have to say, okay, well, how did we get those numbers? I'm giving them to you. So we want to verify. So basically what we're doing is we're checking to make sure that both of the requirements of a probability distribution, which are listed here, are true, okay? So the first thing that we want to do is we want to verify that the probability of each x is between 0 and 1. And this is true, okay? And here's how we know. We're going to go through each one. And I'm not always going to write this down, but I'll write it down for this one. So we're asking ourselves, is 0.09 between 0 and 1? And the answer is yes, it is. Is 0.36 between 0 and 1? Yes, it is. Is 0.49 between 0 and 1? Yes, it is. And it is 0.10 between 0 and 1. Yes, it is. So the first requirement is true. So now we're just going to check the second requirement. And the second requirement says the sum of the probabilities is 1. So we're going to check this, okay? We want to add the probabilities. We want to say, okay, well, the probability that we get a 1, 2, 3, or 4 is 1. That will definitely happen. So 0.09 plus 0.36 plus 0.49 plus 0.10. And this is equal to 1.07, which is not 1. So no, this is not true. Okay, that means this is not a probability distribution. Because, and I'll use the notation here, the sum of the outcomes, the probabilities of the outcomes, is not 1. So the first thing is true, but the second one is not true, the second requirement. So therefore, it's not a probability distribution. Okay, so this is our first case. Let's take another one. Okay, another example. So we're going to consider, this is a 2, by the way. We're going to consider the probability distribution. And this time I'll give you what we're measuring. For the number of overtime hours used by employees of some company, okay? So here's the distribution that you're going to be given. So the number of overtime hours is X. And then we have the probability of X. And the different possibilities are 0 hours, 1, 2, 3, 4 hours, 5, or 6 hours. Okay. Probability of 0 hours is 0.03. 1 hour is 0.06. 2 hours is 0.15. 3 hours is 0.30. The probability somebody takes 4 hours is 0.22. The probability somebody takes 5 hours is 0.16. And the probability that somebody takes 6 hours is 0.08. Okay, so the first thing that we're going to do is verify it's a distribution. So the first part is yes, everything is between 0 and 1. 0.03, 0.06, 0.15, 0.3, 0.22, 0.16, 0.08. Those are all between 0 and 1. Part A, first requirement, satisfied. Part B, we're going to add all of these numbers together. So the sum of the probabilities that's a 0.30. We're just adding all of these probabilities together. And yes, that is equal to 1. So yes, it's a probability distribution. We verified. Okay. Now let's take some other questions. Okay. Let's say that we want to know what is the probability of x equals 5. Okay, in other words, and I won't write this for all of them, but we're asking what is the probability somebody takes 5 hours? And all we have to do is go to our distribution. So we go to our distribution and we say, okay, what's the probability that our employee took 5 hours of overtime? It's just 0.16. Okay. The probability that somebody took 2 hours, and you should stop the video at this point and see if you could answer it on your own. But the probability that somebody took 2 hours, we just go to 2 in the chart and in our distribution, and it's 0.15. But let's say that we want to know what's the probability that somebody took less than 2 hours. Well, less than 2 means that, okay, well, either they took 0 hours or they took 1 hour. That would be less than 2. And in those cases, we just go to the chart and we add together 0.03 plus 0.06. And we get 0.09. Or we could say, well, what's the probability that somebody took more than 3 hours? Well, that means that either they took 4 hours, or they took 5 hours, or they took 6 hours. So the probability that somebody took 4 hours is 0.22. Probability that they took 5 hours is 0.16. And the probability that they took 6 hours is 0.08. So if we add these together, we get 0.46. So the probability that somebody took more than 3 hours of overtime is 0.46. Okay. Or we could say, okay, well, what's the probability that somebody took greater than or equal to 4 hours? And this actually winds up being exactly the same because they took 4, or they took 5, or they took 6. So it winds up being the same. We're just adding together our numbers. If we do one more, we could say, well, what's the probability that somebody took less than or equal to 3? Well, less than or equal to 3 would be 3 hours, 2 hours, 1 hour, or 0 hours. And if we just add these numbers together, well, 3 hours is 0.30, 2 hours is 0.15, 1 hour is 0.06, and 0 hours is 0.03. So if we take those numbers and we add them together, then we get 0.27. Sorry, not 0.27. I did that wrong. I actually knew that that didn't make sense because this should add up to 1, right? Because together they make up all of the numbers. So just that you know, that's how I figured out that it didn't make sense and that I made a mistake in my adding. So it's 0.3 plus 0.15 plus 0.06 plus 0.03. I accidentally did 0.03 twice instead. So this is 0.54. And I know that that's right because when we add these together, it is 1. And this is just a coincidence, right? That together, these make up all of the numbers, all of the outcomes together. Okay, let's do one more example. So suppose that the probability distribution for a quiz is given as follows. So I'm telling you it is a probability distribution, so you do not need to verify it, okay? So this is going to be our last example. Our third example. So our random variable x is the score on the quiz. And then you have the probability of getting that score. And on this particular quiz, you could get anywhere from a 1 to a 5. There is no 0. You can't get 0. So this is 0.16, this is 0.22, this is 0.28, and this is 0.20. And the probability of getting a 5 is unknown, okay? So we're going to ask a couple of questions here. The first is, what is the probability of getting a 5? Okay, it's unknown. Well, here's the thing. We're going to use the verifying to help us because in order to verify, we know that all of the probabilities have to be between 0 and 1. Now, that doesn't really help us find this probability, though. The second thing that we know is that the sum of the probabilities has to equal 1. So if we take the sum of what we know, right? The sum of the probabilities has to equal 1. So if we take what we already know, 0.16 plus 0.22 plus 0.28 plus 0.20, that gives us 0.86. So that means that the probability of x equals 5 is 1 minus that, or 0.14. Okay, because we know that the total sum has to be 1. The sum of the first 4 numbers is already 0.86, so the only way that we could get to 1 is if the probability of getting a 5 is 0.14. Okay, so if we add all of these together now, 0.16 plus 0.22 plus 0.28 plus 0.20 plus the 0.14 that we just found, is equal to 1. It has to be that way or it wouldn't be a probability distribution. Okay. And just for practice, we're going to find the probability. I'll do this in blue. The probability of x greater than 4. Well, the only one where x is greater than 4 is when x equals 5. And we already know from the last problem that we did that that means that it's 0.14. The probability that x is greater than or equal to 3 would be the probability that x is 3 or 4 or 5. So we can just add these numbers. Probability that x is 3 is 0.28. Probability that it's 4 is 0.20. And the probability that it's 5, we figured out, is 0.14. So 0.28 plus 0.20 plus 0.14 is 0.62. If we wanted instead to find the probability that x is less than or equal to 2, well, the numbers that are less than or equal to 2 are 2 and 1. So the probability that it's 2 is 0.22, and the probability that it's 1 is 0.16. So if we take that and we add it together, we get 0.38. Okay, and I want to be clear about what this means. This means that if we looked at a certain number, if we looked at a group of people and we said, what is the probability that out of that group, a person got a 1? So we take the number of people who got 1s over the number of people in the group, and we get 0.16. And we do that with each of these numbers. What's the probability that you get a 2? We take the total number of people who got a 2, divide it by the total number of people in the group. What this is telling us is the next person who takes that quiz, what's the probability that they get something greater than a 4? What's the probability that the next person who takes that quiz is getting greater than or equal to a 3 or less than or equal to a 2? So we're predicting not what already happened. That's what the probability distribution is. What we're predicting is the next person who takes the quiz, what are they going to get? In this case, we're predicting the next person who takes overtime hours. What's the probability that they're going to take 3 hours? What's the probability that they're going to take 2 hours? What's the probability that they're going to take less than 2 hours? That's what we're trying to predict using a probability distribution. Okay, that's it.